Hello everyone, my name is Pawel Olejnik. During this invited talk, I would like to say about some results of our research on the application of a neural network based on a physical model of rotational contact for determining asymmetric friction law. During this presentation, I'm going to introduce a physics-informed neural network approach for modeling friction, positioning it as an effective method for friction estimation. We use experimental data from a double torsion pendulum system featuring discontinuous dynamics, which was utilized for training. The results highlight the network superiority, providing a more precise representation of stick-slip phases at the contact zone. In summary, the presentation includes a case study. The white box friction models can be classified into two categories, static and dynamic models. The static column friction is mathematically expressed with the use of SGN function as given in equation 1. An extension of the column model is shown in equation 3, where Fv, the viscous friction dependent on the viscous friction coefficient, appears. In the next iteration, we find the Strebeck model, which is formed by combining Coulomb, viscous, and Strebeck effect. The Strebeck effect term is visible here in equation 4. Here are the subsequent realizations in the graphical form on the characteristics dependent on the relative velocity of motion. Now let us talk about the dynamic friction models. The dual friction model stands as an early dynamic one, given in Formula 5. Here, the friction force is dependent on variable z, which is given here by a first-order differential equation dependent on the relative velocity, gamma and beta. Gamma and beta are non-dimensional, but gamma is here. The development of the previous dynamic model is the Lugre friction model given by Formula 6. And the third one considered in our overview is the generalized Maxwell slip, which can be represented by the following figure. The equations of the model are here omitted. In this section, in this part of the presentation, we shortly summarize the discussed static and dynamic friction models. And for instance, the column friction model has a friction force proportional to the normal force. The parameter is coefficient of friction and features simple, readily applicable, but of limited accuracy. When we add viscosity, and then the mathematical function is a combination of two. The parameters are coefficient of friction and viscous damping, but features, in the features we see that it adds damping, is useful for specific cases, and has moderate accuracy. The Strebeck friction model models sliding speeds and has better accuracy in some cases. The dynamic friction models can be concluded as follows. The most simplest has linear springs and dampers. In parameters, we could enumerate spring constants, damping coefficients, and the features are varying velocity, rate-dependent effects, calibration. Lugre friction model introduces nonlinear differential equations with observer. In parameters, we enumerate static friction, viscous friction, and the features capture static and dynamic friction and also pre-sliding. Generalized Maxwell slip can be also interesting because in the features we could enumerate viscoelasticity, slip behavior, and material compliance. Looking at the field of use accuracy, the static models are simple and applicable, but have limited accuracy. The dynamic models are accurate for varying velocities and complex dynamics. Now, in the features and complexity, the static models are easy to use and lack dynamic features. Dynamic models include rate-dependent effects, pre-sliding, and material compliance. Basically, friction models can be static and dynamic ones. Static are Coulomb model, Coulomb plus viscous, and Coulomb plus Triboc effect. The dynamic models are Dahl, Lugre, or even Maxwell slip. In the first case, the static models allow for basic analysis and include negligible velocity effects. The dynamics models allow for real-world systems modeling, varying velocities, and even complex behavior. In the domain of friction modeling, the static models typically assume the absence of microscopic effects in the pre-sliding regime, while dynamic models account for both microscopic and macroscopic friction effects during both the pre-sliding and sliding regimes. As a result, dynamic models are better suited to capture the microscopic surface displacements that occur during the pre-sliding phase. We observe that the mentioned models take on diverse forms that I've mentioned, ranging from less to more complex, and through appropriate manipulation, sometimes even by combination, enable modeling friction in a black box approach. We acknowledge that there are many more such models, but we wanted to highlight the difficulty in selecting the appropriate description for modeling a specific physical phenomenon. The challenge arises from determining the parameters of these models in various operating regimes of dynamic systems with friction. And therefore, in the subsequent part of this presentation, we propose the use of neural networks, which will develop a universal, something like a universal approximator for friction force or torque, and consequently friction characteristics. In our numerical simulation study preceding our experimental identification, we consider a reduced model of a double torsion pendulum system shown in figure 5. Here we see an excitation from below. We see an excitation of the column via the spiral spring. The column rotates about this angle, about this top pin. On the bottom of this column, disk of mass moment of inertia J2 is placed, of which motion is also restricted and occurs between these two beam springs. The planar contact is created here. Equation 9 shows the mathematical model of dynamical behavior of the disk, of which angle is phi2. Inputs to the system are acceleration of the column from below, friction force between them, elasticity force, and damping force here. Numerical simulation is conducted at the following parameters. various friction models are compared, and in figure 6 we see friction forces versus velocity of the disk. So we can see that its behavior is mostly different about zero relative velocity. In rotational mechanical systems, friction torque and angular velocity are measured. So at constant velocity or angular velocity, the force or torque input to the system equals the friction force or torque. So we have such equation. In our case, tau f will be identified. And now we are at the data-driven friction models. So there are several important concepts to consider when developing a data-driven model. So it is a system excitation, time domain and frequency domain data, and so on. Schematics in figure 8 presents a gray box system modeling approach. We begin from the experiment part, where a physical system, in our case in open loop, is found. Then we collect experimental data. After that, we define a model structure with a dynamic model and friction model with some input like unknowns and some necessary equations. Then we switch to identification algorithm, where least squares genetic algorithm could be applied. Having it identified, we perform model validation. Schematics shown in figure 10 presents black box friction modeling approach. Similarly to the previous case, we start from the experiment, collecting the data, then after the pre-processing the data, we use neural networks. Here we see a traditional case, and in the physics-informed neural network, we having the desired output, so we compute NSC and additionally physics laws. Then using a backpropagation algorithm, we update the network parameters. In the output, we can find the dynamic model or even dynamic and friction model. The particular jth neuron of the neural network has a standard form with inputs, weights, biases, a part of summation, then application of activation function, and finally the output OJ. An artificial neural network is typically trained using supervised learning. During each iteration of training, the network is fed with an input and its output is compared with the expected target using a loss function, which measures the discrepancy between the predicted and target output, for instance, using the following formula. The physics-informed neural network can be used to solve ordinary and partial differential equations. For example, given a first-order differential equation below. The solution of equation 19 means while dependent on t can be approximated by a neural network as follows, where n tilde is the approximation of the solution. The derivative of the network output is computed with respect to its inputs through automatic differentiation. As a result, the new loss function that is used to optimize the neural network is composed of two parts. LS is the loss of the solution, and LEQ is the loss computed based on the system equation. The estimation scheme of the friction moment can be explained based on the following block diagram. The PWM control signal is fed into the stepper motor controller. As a result, a friction moment tau is generated, acting on the column pendulum. In response, a rotation by an angle phi 1 occurs, affecting the upper disk pendulum. In response to this excitation generated through the friction on the contact surface of both bodies, the disk rotates about phi 2 relative to the column. Both state variables of the 2 degree of freedom pendulum are used by the algorithm of identification of the friction moment and the constant mass moment of inertia of both bodies. We also obtain weights biases for the network, creating the identified pin model. Using this model, we calculate the friction moment, and as a result we find the friction model as well. The identified phi 2 hat and actual response phi 2 tilde of the second pendulum are used to calculate the estimation error. And here we have the experimental test stand. Parts of the stand correspond to the physical model presented earlier. One could add that the angle of rotation of the disk and angle of rotation of the pendulum are measured with the use of a Hall effect device and transferred to the controller. Two time histories of angular displacements phi 1 and phi 2 after the data acquisition are shown in figure 15. Here we see the columns motion and response of the disk placed on it, characteristic stick slip motions. So we have a slip, stick, slip, stick, slip, and stick is seen. We are going to compare our methodology with an existing one, and therefore the Nelder mid-simplex algorithm was used. After application of the algorithm, a set of parameters of the friction model is found. Estimation of the friction torque and model parameters follows according to the pin algorithm applied. We start by initiation of the algorithm, load the training and test dataset acquired after the measurements, create and configure two networks N1 and A2. N1 will approximate phi to finding its approximation, and N2 approximates tau f, frictional torque. Then we add some trainable parameters to N1, add the physics of the system to the network loss computation. As expected, the total is a sum of both losses. Then we define the hyperparameters, means number of hidden neurons, number of layers, epochs, learning rate, and so on. Then we train our model to find N1 and N2 using an Adam optimizer. We validate and then save our model. Here are the hyperparameters used in our computations. A few words is the loss function used in training N1, and it is the mean squared error of the predicted disk pendulum angular rotation, while the loss function of N2 is the computation of residual of the system derived from Newton's second law of rotation, yeah, where tau is as follows. It is the input torque coming from rotational motion of the column pendulum. Tau F is the friction torque being sought. J1 and J2 are the mass moments of inertia of the column and the disk pendulum. Now let us proceed to the analysis of the results. In figure 17a, we have a time characteristic of the rotational motion of the pendulum in the form of a disk. The red line represents the recorded actual trajectory of motion. The gray line is the response of the numerical model obtained using parameters calculated with the Nelder-Mead algorithm, and the blue line is the response of the model obtained using pin-type network. It is evident that the latter response better approximates the real behavior of the investigated dynamic system, capturing, for instance, smooth transitions to the settling or the stick phase more effectively. The charts in figure B demonstrate the similarity of friction moment characteristics, while the prediction error here of the dynamic model is clearly in favor of the pin network. In figure 18, we find the estimated non-symmetric friction torque characteristics. It is seen that the characteristics is asymmetric versus the vertical line crossing zero relative velocity of motion. The left-hand side proves linearity, while the right-hand side of the characteristics a non-linear component in the viscous friction part. So we also notice different values of breakaway torques, which are slightly different. So worth noticing is that the characteristics is an experimental one, partially experimental one, means that the phi 2 dot is the measured relative velocity on the experimental stand, but the friction torque is the estimated torque with the use of our neural network. Conclusions. Thank you for your attention.